Good afternoon, Abstract Algebra. This is our second problem-solving session of the semester, and my goal for our session today is to take a look together at some problems that are from our third chapter of the course. This is the chapter where we begin to think about how to locate smaller group structures, what we call subgroups, inside of larger groups, and then also to think about how to tell different groups apart. This is ultimately going to be our most important question of the semester, which is, if you give me two groups, how can I tell whether or not those groups have the same structure as one another, or whether they might in fact be different? So what we want to do, ultimately, is build a repertoire of tools that we can use to tell different groups apart, to be able to spot the differences that actually matter. So if you're watching us live and you're a part of my class this semester, feel free to drop questions in the Slack chat as we go along, and I'll be able to see them and respond to them in real time. If you're not a part of our course and you're watching right now, you're also, of course, welcome to drop any questions into the Twitch chat. That will get to me either way. And if you're watching this video after the fact via YouTube, you can, of course, use the timestamps in the video description that are right underneath me here to jump around to different spots in the video so that you don't have to watch the whole hour-long thing if you're just coming for one or two different topics that we happened to talk about today. So let me just make sure that the stream is actually working, because I'm doing this from my office, and for some reason streams from the office tend to be a little bit less reliable than the ones that I do from home, but that is how it is. So I think we're in good shape and we'll get underway today. So let's take a look at what we have to work with. So I've selected a sort of a smattering of topics from the material that we're talking about, with the hope that it will give us the chance to kind of see some problem solving across the broad spectrum of different types of questions that we're looking at. They're also chosen with input from you, from specific student questions that I got about this material. So what I actually want to do to get us started is to take a closer look at what we call the multiplicative groups, the groups UN. So I'm going to do that by putting a question up on the screen that was taken from our textbook. This is our Judson Online textbook. This will both give us an opportunity to think about the U groups, but also to think about some of the other questions that we hold dear in this chapter. This is question number 8 from chapter 3, which asks us to list all of the cyclic subgroups of the group U30. So, of course, the first thing we need to do is we need to decide for ourselves, what does U30 actually mean? So, good news and bad news. The good news is that the U groups use arithmetic that is more or less familiar to us. When I say U group, the U here stands for unit. So what this means is units modulo 30. And the word unit, when used by somebody in abstract algebra, just means those things that have multiplicative inverses. In other words, these are the integers which, when I multiply them by some other integer, I'll be able to arrive at the multiplicative identity when that multiplication happens modulo 30. So here's what that means, kind of. So the U groups are the spiritual successors to the Z groups, right? If we're talking about the Z groups, like Z30, this would be the group of equivalence classes of integers modulo 30, with the operation of addition, mod 30. And so for the Z groups, we would think of the integers being arranged around the face of a clock, 0, 1, 2, 3, 4, and so on, 15, 16, 17, up to 29. And then once we get back to 0, it's the same place as 30, and so on and so forth. And so for my Z groups, I can do an operation like, well, what is, in this group, 18 plus 23? Well, in this group, 18 plus 23, if I add those two things as integers, that's going to give me 41. But then I'm going to reduce that thing mod 30 and conclude that it's equal to 11 mod 30. Right? And so In the Z group, Z30, this is the kind of arithmetic that we do. The arithmetic is all driven by addition. Well, in the U groups, the elements are more or less the same. We're going to have to talk a little bit more carefully about that in a minute. But the most important thing is that the operation in my U groups is not addition. The operation is multiplication. And again, using a modulus, which in this example is mod 30. So if, for example, I were to do 18 multiply 11, I would do this as integers. What would I get, 198 or something like that? And then I would reduce this mod 30, which mod 30, that's going to give me 18. Mod 30. Right? So it's modular arithmetic, just with the operation now being multiplication instead of addition, the way that it was when we talked about the additive groups, mod n. These are the multiplicative groups, mod n. But you notice something right off the bat with just this calculation that I did. 18 times 11 is equal to 18. And something fishy should jump out at you immediately. Namely, 18 times 11 equals 18 would seem to suggest that 11 is an identity element. Because look at what happened. It multiplied 18 and it left 18 unchanged. Right? 18 times 11 is somehow equal to 18. That shouldn't sit well with us. After all, if 11 were an identity element, it wouldn't be the only one. Because the number 1 would also be an identity in any U group. After all, multiplication by 1 always leaves anything unchanged, whether that multiplication happens at the level of integers or whether that multiplication happens with a modulus attached to it. But this should give me indigestion, right? Because we know for sure, based on the basic properties of groups that we learned in Chapter 2, that a group, so a set of elements with a binary operation that at least satisfies the identity property, a group may only have one identity element. The identity element in a group is unique. And so right away, we know that something is fishy here, right? That we can't possibly have my group be the group of integers with multiplication mod 30. It can't be that simple, because if it were, both 11 and 1 would appear to act like an identity element, at least when they multiply the number 18. So there is a little more to the story for the U groups. Let's talk a little bit more about what the rest of that story is. To do that, let's again focus on 30 as being my modulus here for the moment. And if this were the additive group, mod 30, we would have all of the residue classes mod 30 from 0 up to 29. Those would all be elements. Let me jump up to 24, let's say 25, 26, 27, 28, and 29. These are all 30 of the different positions around the 30-hour clock face, if you like, right? But there's a problem if multiplication is going to be my operation. Multiplication mod 30 is the operation. Let's ask ourselves, what do we know about multiplication mod 30? Well, what we know about multiplication mod 30 is inherited from what we know about multiplication of integers in the first place. If this multiplication is the operation, then we know we're going to get the associative property to hold, for sure. We won't go through the process of actually verifying that, but associative property holds for just the ordinary multiplication of integers and remains true when we reduce mod 30. We also know that that operation has the commutative property. After all, multiplication of integers is commutative. X times y is equal to y times x when x and y are integers, and times means multiplication. So not only is this an associative operation, it's also a commutative operation. But when we poke a little bit further, let's think about the identity property. What would the identity element in my group have to be if my operation is multiplication? Well, as we were saying a minute ago, when multiplication is our operation, at the level of integers, there's a prototype for what the multiplicative identity in the group of integers is, and that's the number 1. So here's my identity. After all, 1 times anything, whether that happens on the left or the right, after all, multiplication is commutative, 1 times anything is going to give me that thing. It's going to leave that thing unchanged. So 1 is going to be my identity element. So as long as 1 belongs to my set of elements with the operation being multiplication mod 30, then we'll be in good shape. So we'll put a check mark there with the, now we have a restriction, right? We need to have 1 be a part of my group in order to meet the identity property. So the sticky part, well, let's do one more property here before we get to the sticky part. What about closure? If I multiply 2 integers and reduce mod 30, is their product still going to be a residue class mod 30? And the answer to that is yes. Right? Multiplication of integers is a closed operation, and when I reduce that mod 30, we still get a closed operation. So closure is not a problem. So the sticky part, the part that actually causes us to rethink our place in the universe a little bit, is the inverse property. After all, if I were to ask you, for example, what is the inverse of, I don't know, let's pick 7. What is the inverse of 7 in this algebraic structure where my operation is multiplication mod 30? How would you answer that question? Well, the naive answer, right, the naive answer is that if I'm looking for an inverse for 7, what I'm trying to do is solve the equation 7 times what, let's say, call it x, right? 7 times what is equal to the identity element in my group, and we decided that the identity element in our group is equal to 1. And so the naive answer is, let's just divide both sides of this equation by 7, as though this were an equation describing rational numbers rather than integer residue classes mod 30. So the naive answer is, oh, x is just 1/7. The problem with this naive answer is that it's nonsensical from the abstract algebra perspective, right? Because this notation, 1/7, is meaningless unless somehow 1/7 can be identified as an element in my group. So don't let me catch you writing something like 1 divided by 7. One of the habits I've been trying to break you of early this semester is thinking about division at all, right? We should always think about division as just being an instance of multiplication by an inverse, right? So multiplication here being the operation in our group, and inverse being whatever it is that meets the inverse property. So if I just write x as just 1/7, that's not telling me anything that I don't already know. That 1/, just means inverse of, after all, right? So this naive way of thinking about it is probably not going to help. So what I want to do instead is I want to look for ways of solving this equation, 7 times x is equal to 1. And again, because our operation here is multiplication mod 30, we can add in here congruent mod 30. Let's try some different values of x to see if maybe we can stumble upon the inverse. So for example, let's say I try x is equal to 4. Well, 7 times 4 is equal to 28. That's not equal to 1 mod 30. Right, so 4 doesn't quite do it. What about 5? If I try multiplying 7 by 5, that's going to give me, as integers, 35, but then I reduce that mod 30, and I get 5. Okay, so there's again another bit of a problem, because it looks like 5 is acting like, or 7 is acting like an identity element when it multiplies 5. So let me put a big question mark here. So that feels like something we shouldn't allow to happen somehow. Let's keep going. So we can sort of keep plugging away at this for a while until we find, if it's possible, something which when I multiply by 7 is going to give me something which is congruent to 1 mod 30. But let's unravel this equation that I just wrote down here. Let's unravel this just a little bit and talk really briefly about some elementary number theory. Because one of the things that you study when you study number theory is whether or not equations that are subject to a modular reduction, like our reduction mod 30 that we're doing here, to study whether equations of those types even have solutions. And if they do have solutions, how many solutions do they have? How do we find them? And so forth. So what I want to do is unravel this equation. If 7x is equal to 1, mod 30, if it's congruent to 1 mod 30, I should say, what that means is that 7x minus 1, so if I subtract this 1 from both sides, would be congruent to 0 mod 30. That's another way to think about what this equation is saying. But for something to be congruent to 0 mod 30 means that that something is a multiple of 30. So what I'm looking for in my x here is some integer which has the property that 7 times that integer minus 1 is a multiple of 30. And to operationalize that as an equation, 7x minus 1 is going to equal 30 times n for some integer n. Right? So for some integer n, 7x minus 1 is going to be 30 times n. And if I rearrange this to get the 30n on one side and the 1 on the other side, so I'm just going to trade places, what I have is a type of equation that number theorists call a linear Diophantine equation. 7x minus 30n, so on the left side of the equation, I have a linear combination of two integers, x and n, and on the right-hand side, I have the number 1. And so the one bit of number theory that we're going to plug into this mix is as follows. Number theory says that this has a solution only when the greatest common divisor of 7 and 30 is equal to 1. 1 being that right-hand side, and 7 and 30 being the coefficients on the left-hand side. Right? So if we take a step back from that for a minute, what this is telling me is that I'm going to be able to find the multiplicative inverse of 7 mod 30 if and only if the greatest common divisor of 7 and 30 is equal to 1. In other words, the word that we often use for this in number theory is that 7 and 30 need to be relatively prime. They have to have no interesting common factors. And it just so happens that 7 and 30 are indeed relatively prime, one to another. And so according to this, if we believe this statement from number theory, we should be able to find a multiplicative inverse of 7. It should exist. And so finding it is just going to be possibly a matter of trying some different values. And so we may be able to get more sophisticated with this later on. Or if you take a number theory class, you may be able to get more sophisticated as well. But I'm just going to just do some manual calculation here. Just going to try and get Sage, our computer algebra system, to do some calculation for us. So it's been a little bit slow because we're also live streaming at the moment, but it should pop up my Sage cell for evaluation here in just a second. Wow, this thing is really getting bogged down here today. Where did it go? I don't know why this is not cooperating here. Here we go. Let me expand this up a little bit so you can see it more clearly in the video. All right, so what I want to do is I just want to I just want to try some things. So let's say we take x equal to 3, and then I want to know what is 7x modulo 30. So 7x mod 30 when x is 3 is 21. Right, so that's clearly not going to do it. So I want to try some different values. If I try, for example, 13. Uh-oh, already we have it. So when x is equal to 13 and I multiply 13 by 7, 13 times 7 mod 30 is going to give me something which is congruent to 1. And if you don't believe that, just do 13 times 7. 13 times 7 is 91, and 91 is indeed one more than a multiple of 30, because after all, 90 is the multiple of 30. So we have found, a very long way around, that indeed 7 does have an inverse, mod 30. Its inverse is 13. So coming back to our scratch work here, 7 times 13 is equal to 1, congruent to 1 mod 30. And that was possible, once again, if we believe the result from number theory, it was possible because 30 and 7 were relatively prime. And another way to think about that is that what we just learned was that 7 times x minus 30 times n is equal to 1 has a solution because 7 and 30 are relatively prime, and it turned out that the solution was x equals 13 and n equals 3. Right. So here was my inverse of 7 mod 30. Okay. All right, so all of that was a roundabout way to say that in order for this inverse property to hold for my multiplicative group mod 30, every one of the elements in my group needs to have a multiplicative inverse. But if we believe the result from number theory, we know that that's not always going to happen. And so the observation is this, that only those equivalence classes mod 30, only those what we call residues mod 30, that are relatively prime to 30 will have multiplicative inverses at all. And by the way, that's going to be another thing that we kind of are going to be able to appreciate when we actually do this problem that was asked here, list all the cyclic subgroups of U30. So what that tells me is that all of these 30 different elements that belong to the group Z30, all of my additive equivalence classes mod 30, 0, 1, 2, 3, 4, 5, up to 29, not all of these are going to be able to be elements of the multiplicative group U30, because not all of them are going to have multiplicative inverses mod 30. Only those that are relatively prime to 30 will. So what that tells me is that I have to go through and erase anything from this list which has a factor in common with 30. Erase anything that has a common factor to 30, other than, of course, 1. 1 is always a common factor. So 2, for example, we have to get rid of, because 2 has the common factor of itself, 2, with 30. So I have to get rid of 2. For the same reason, I have to get rid of every other multiple of 2, because all the other multiples of 2 are also going to have common factor of 2, at least, with 30. So 4 has to go, 6 has to go, 8 has to go. Up on the top end, 24's got to go, 26 has to go, 28 has to go. All of those have a common factor of at least 2 with the number 30. So they're not relatively prime to 30, and therefore none of those things that I just erased would have had a multiplicative inverse mod 30. I have to do the same thing also for, for 3, because 3 has a common factor of itself, once again, 3, with the number 30. And so I can't let 3 be a part of my group because it won't have a multiplicative inverse. For the same reason, 9 and 27 are not going to have multiplicative inverses, so I have to get rid of them also. So pretty quickly, we're getting rid of a lot of things that we thought may have been able to be elements of this multiplicative group. Likewise with 5. So even 5 has to go because 5 is a factor of 30. Likewise 25. So there's not a lot that ends up surviving, but 7 does. We actually saw concretely a minute ago that 7 does have a multiplicative inverse, namely 13. So 13 is actually going to be also one of the elements in here, because 13 and 30 also have no common factor other than 1. 11 is another integer which has no interesting common factor with 30. And then we start to run out of others pretty quickly. The last one I want to ask about is, what about 0? Can 0 belong to my multiplicative group? And the answer to that is also no. We can't have 0 be a part of my group. Because even though we can't use this number theory explanation about it not being relatively prime, what we can say for sure is that 0 will not have a multiplicative inverse. Not just mod 30, but mod anything, right? Even as an integer, there's no way, even as a rational number, there's no way to multiply something by 0 and arrive at 1. So 0 also has to go for kind of a different reason, but it's really the same reason, that we can't make 0 satisfy the inverse property. We're not going to have a multiplicative inverse for 0. So at the end of the day, what ends up surviving as the elements of U30? I don't think I quite have them all here, but 1 survives, 7 survives, 11 survives, 13 survives. No even number survives, no multiple of 3, no multiple of 5. The next one up I think that survives is 17. 17 has no common factor with 30. Also 19 ends up surviving. But 20 is out, 21 is out, 22 is out, 23 is in, because it's prime and therefore has no common factor with 30 other than 1. But then 24 is out because it's a multiple of 2. 25 is out because it's a multiple of 5. 26 is out because it's a multiple of 2. 27 is out because it's a multiple of 3. 28 is out because it's a multiple of 2. 29 is in because it has no interesting common factor with 30. And then I think we're done. Whew. So what we've arrived at now is a complete list of all of the elements in the group U30. 1, 7, 11, 13, 17, 19, 23, 29. Those are all of the numbers that are less than 30 and that are relatively prime to 30. So what we can say, for example, is the order. So now here come our new vocabulary words from this chapter. The order of the group U30 is evidently 8, because we've listed all of the elements of this group just explicitly at the top of the screen. Right? There are 8 elements in this group, so the order of my group is 8. But how could we, if we want to generalize this, this is the number of integers that are less than 30. Let's say the number of natural numbers, so that we don't have to worry about negatives or 0. The number of natural numbers less than 30 that are relatively prime to 30. So that's kind of the general answer to the question, how many elements does a multiplicative group mod n have? It's the number of natural numbers less than n that are relatively prime to n. And that is not an easy, unfortunately, there's not an easy formula to write down that explicitly for any value of n is going to let us compute this number, the number of natural numbers less than n that are relatively prime to n. But this is a super important calculation for us to do, because it tells us the size, the order of these groups. And in number theory, it tells us a lot of other really interesting and important stuff as well. And so this has a name attached to it. This is called the Euler phi function. Phi of 30 is equal to 8. And that is a definition. That's not a result. This is what the Euler phi function means. The Euler phi function means how many natural numbers less than blank are relatively prime to my blank. So when I feed the Euler phi function the number 30, the answer that comes out is 8, because there are 8 natural numbers less than 30 that are relatively prime to 30. If we want to, we can find values